Now, the main problem with the localized electron model is that electrons are localized in that particular model. In real life, we know that electrons are free to move. This is most apparent when we can draw more than one Lewis structure and we have to apply the concept of resonance to our Lewis structures. Even with resonance, bonding descriptions for several molecules fall apart. So we're going to go ahead and combine the simple views of localized or Lewis models with our delocalized characteristics of molecular orbitals to get a more complete picture of bonding. And then we'll make a few comments about photoelectron spectroscopy. Now, if we look at ozone O3 or nitrogen trioxide NO3, we know that we have our sigma bond between our 3 oxygens in ozone, and then a pi bond, which can be drawn between 2 different oxygens and our central oxygen. So that pi bond moves. The electrons in the pi system are moving. We see the same thing in nitrogen trioxide. Our sigma bond is always present, but the pi bond rotates between nitrogen and different oxygens. Again, we have various resonance forms where the electrons are resonating between different atoms. They're delocalized over our molecule instead of being localized between a set of atoms. In the idea of delocalization, we use this to describe molecules that require resonance in their Lewis structures. In molecules that require resonance, it's the pi bonds that most clearly are delocalized. The sigma bonds are localized between 2 atoms. The p orbitals, which are perpendicular to the plane of the molecule, are used to form the pi molecular orbitals. The electrons in the pi molecular orbitals are delocalized above and below the plane of the molecule. If we look at the benzene molecule, it consists of a ring of 6 carbon atoms with 1 hydrogen atom bound to each carbon, as shown in figure A. Notice in figure A, the carbons don't have octets of electrons. Each carbon has a double bond, and the double bonds rotate around the ring, alternating double, single, double, single, double, single. We can draw that in 2 different ways by just pushing the electrons around the ring. We say that the electrons are resonating around the ring. They are delocalized over the pi system. All of our carbons are sp2 hybridized with approximately 120-degree bond angles. The unhybridized p orbital on each carbon is perpendicular to the plane of the ring, and it's the electrons in this pi system that are delocalized above and below the ring. Here we see the sigma bonds using our sp2 hybridized orbitals on carbon. Here we see the unhybridized p orbital on each carbon atom perpendicular to the plane of the ring. In figure B, we can see the ring of electron density, which will either be above or below the ring system carbons, caused by the overlap of that pi system. In that pi system, the electrons resonate between carbons around the ring. This results in no isolated double and single bonds. Instead, we have a bond length and a bond strength that's somewhere in between a double and a single bond. All of the bond lengths and bond strengths are identical in this ring system. This is what's referred to as aromatic ring stabilization. If we look back at our nitrogen trioxide ion that we saw earlier, we can see the spread of electron density delocalized over the molecule. It does not require a ring system to have this resonating delocalization of electron density over our molecule. Now finally, photoelectron spectroscopy is a method which can be used to determine relative energies of electrons in individual atoms or molecules. In photoelectron spectroscopy, high energy photons are directed at a sample and the kinetic energies of the ejected electrons are measured. And we can relate this then to molecular orbital energy level diagrams.